Okay, so we started our discussion on allocation of free inodes to newly created files or newly created directories. And we have seen that to facilitate this job, a list of free inodes is kept in the superblock, which is called a superblock free inode list. So the superblock free inode list is kept like this. The superblock free inode list has a finite capacity. So normally when I have sufficient number of free inodes on the disk, then the free inode numbers will be kept in the superblock list to its full capacity. The highest numbered inode, usually it is the highest numbered, but it may not always be so. So usually the highest numbered inode is called the remembered inode, and this is the at the tail or end of this superblock free inode list. So whenever a process requests for a new inode while creation of a file or while creation of a directory, an inode will be taken from this superblock free inode list and it will be allocated to the process requesting for it. Finally, when all the inodes which are there in the superblock free inode list are allocated, and it comes to a situation that this last inode, which is called a remembered inode, is to be allocated, at that point the superblock free inode list will be empty. So while allocation, if the kernel finds that the superblock free inode list is empty, in that case what it will do is it will just recall this remembered inode, knowing that the other free inodes may be available after this. Okay, so it will read free inodes and place the numbers of these free inodes in this superblock free inode list again until the superblock free inode list is full, it is full to its capacity, or there is no more free inode on the disk. So once this superblock free inode list is set, then only this inode number, in this case it is 499, will be allocated to the requesting process. Okay. Similarly, we have said that whenever a process releases an inode by deleting a file or by deleting a directory, in that case, this inode, now the type field of this inode has to be marked to be 0. So that has to be available to other requesting processes. So in that case, what you have to do is when this new inode is freed, then first what is checked is whether there is whether this newly freed inode is less than the remembered inode number or not. So if it is less than the remembered inode number, in that case, this remembered inode will be replaced by this freed inode. Okay. So accordingly, we can write an algorithm similar to as we have written in case of allocation of free inodes. We can write an algorithm for freeing an inode is like this. So we can write an algorithm. Let us call this algorithm as ifree. Okay. So now a new inode, an inode which was previously allocated, is being freed. So obviously the number of free inode counts has to be incremented by 1. So the first step that you have to do is increment free inode count. Then you check if superblock locked or not. If the superblock is locked, then you don't do anything, simply return from this algorithm. Okay. In earlier cases, we have seen that when the process requests for an inode and it finds that the superblock is locked, then the process goes to sleep mode. Now in this case, the process does not go to sleep mode. It simply returns from this freeing process. Now if the superblock is not locked, then what you have to do is you have to check if superblock inode list or free inode list is full. Okay. So if the superblock free inode list is full, then what you have to do is we have to check that if inode number that is being freed is less than remembered inode then you have to set the remembered inode is equal to the input inode number. That is the inode number which is inputted to this algorithm. Okay. Then if the inode number is less than the remembered inode, in that case we have to set the remembered inode as this new inode which is becoming free. Okay. Else store inode number in superblock inode list. Okay. So if the superblock free inode list is not full, then this new inode number will be placed in the superblock free inode list. In case it is full and the inode number is less than the remembered inode, then the remembered inode has to be set to this new inode number. And with this, you can return from this algorithm. Okay. So this is the entire process which has to be done while an inode is to be freed. Okay. So with this we have seen that when a process creates a file, then how the new inode is to be allocated to the file, or when the process deletes a file or deletes a directory, then how the inode number is to be freed, and it has to be reflected in the superblock free inode list if possible. Okay. Now when a process opens a file or a process opens a directory, then naturally there will be some modification in the file or some modification in the directory. That means the process will require the data blocks. Earlier what we have seen is the process needs an inode for every file or every directory. Now to store the content of the file or to store the content of the directory, the process will need data blocks where the content of the file will be stored or the content of the directory will be stored. Okay. So as in case of inode allocation, when you allocate a new inode, a new free inode to a requesting process, similarly the process will request for new and new data blocks which are free. Also the process will release the data blocks if the file size is reduced, or even in case the file is deleted, then all the data blocks which were occupied by the data of that file has to be released and they has to go to free data block list. So again, to help this process of allocation of data blocks or removal of data blocks, the superblock again contains a list which is called a superblock free data block list. Now the way the superblock free block list is maintained is different from the way in which the inodes are maintained. Okay. So when you say that a superblock free block list, okay, we can assume that it's a single block which will contain a list of other data block numbers which are free. So this part is similar to the superblock free inode list, where the superblock free inode list contains a list of free inode numbers on the disk. Okay. So the superblock free data block list will appear something like this. This is maintained, I mean, it is not only the superblock free block list, but all the free blocks are maintained in the form of a linked list. Okay. So at a particular instant of time, if I assume that these are the free blocks which are contained in the superblock free block list. Say for example 40, 45, maybe 65, say 70, 71. So this is a block within the super block which contains a number of serial numbers, a list of serial numbers of different data blocks which are free. Okay. Now this last one, that is number 71, it is actually a pointer to block number 71. Okay. So this block number 71 in turn will contain a number of entries where every entry is a serial number of a number of other free blocks in the file system. Okay. So it is something like this. After 70, maybe the free block which is available is 80, that may be 81, then maybe 87. So this may be 100, 110, and so on. Okay. So what is this? This is being maintained in the form of a linked list, where this 71 means it is a pointer to block number 71. Block number 71 will again contain additional list of other free blocks. Okay. So this block, the block number 71, this is actually block number 71, this is called a link block. Okay. Similarly, this 110, this is again a pointer which is pointing to block number 110. Okay. Block number 110 will in turn contain a list of numbers which are serial numbers of other free blocks in the file system. So this may be something like say 150, 200, 210. So this way this may be 350, this may be 340, and so on. And this is actually the content of block number 110. Okay. So this way it will continue. Again, block number 350 will contain a list of other serial numbers which are the serial numbers of other free blocks on the file system. Okay. So unlike in case of superblock free inode list, where we didn't have to use any such linked list structure, the list in the superblock of free inodes is a simple list. Whenever we find that that list is empty, we have to get the list of other free inodes on the file system to be filled up in the superblock free inode list. In case of superblock free data block list, the structure is something like this. It has to be maintained in the form of a linked list. Now, why do we need such a complicated structure for disk blocks, for data blocks, which is not needed in case of inodes? Can you answer? It is simply because of a regular structure of inodes. See, every disk inode has got a fixed number of fields. Every field will need fixed number of bytes or fixed number of characters. That means the size of every disk inode is constant. They are of uniform size. Being they are of uniform size, any field of a disk inode can be accessed very easily. And we know that the type field of the disk inode indicates whether the inode is free or it is not free. If the type field is 0, then we know that inode is free. If the type field is non-zero, then it may be an inode allocated to a regular file, or it may be an inode allocated to a directory. Okay. So just by checking the type fields of different inodes, we can easily find out whether the inode is free or inode is already allocated, which is not possible in case of data blocks, because a data block is likely to contain any arbitrary data. So even if we set the sum field, which may indicate whether the data block is free or the data block is not free, but there may be some data which matches with that particular bit pattern or that particular character. Okay. So by simply checking the data blocks, physically we cannot say whether the data block is free or the data block is not free, which we can do in case of an inode. And that is possible because of an well-defined structure of the inodes, which is not possible in case of data blocks. So for data blocks, I need a special kind of arrangement like this to tell me that what are the data blocks which are free. Okay. And it is the responsibility of a system function called make file system you must have heard about this function, MKFS or make file system. So it is the responsibility of this make file system function to arrange or organize all the free data blocks in the form of a linked list like this. Okay. So all the data blocks on the file system will be part of this linked list. Some of the data blocks will be link blocks. Say for example, block number 71, it is a link block, but block number 100 is not a link block. Here the last entry was 110, block number 110. So block number 110 is again a link block which contains a list of other free blocks in the file system. Okay. And this linked list start from this super block free block list. Okay. So this first block is a component of the super block. This is also a link block. So a block in the super block is also a link block which contains a number of free block numbers, list of free block numbers. Last entry in this block is a pointer to the disk block, to the data block, which is pointed to by this entry. So here it is 71. So it points to block number 71. Block number 71 is again a link block, which contains a number of free block numbers, a list of free block numbers. Again the last entry, which is block number 110, this points to block number 110. So block 110 is again a link block, which in turn contains a number of a list of other free data blocks on the file system, and this way it continues. Okay. Now how this free block allocation will be done in this case? Whenever a process requests for a free block, so by now it is clear that every data block which is free must be part of this kind of linked list, each and every data block. If there is any data block which is free but it is not a part of this linked list, that data block can never be allocated. It will be wasted. Okay. So while allocation or while freeing a data block, we must ensure that the data blocks, whenever it is free, that has to be put in some place in this linked list. For allocation it is not a problem because you are simply taking out the block from this linked list. But when you are freeing a block, it must be ensured that the free block is returned to this linked list. Okay. Now the allocation process is very simple. Whenever a process requests for a free block, okay, it goes to the super block free block list, takes out this block, in this case it is block number 40, gives it to the requesting process. Next time a process requests for another block, it takes out this block number 45, gives it to the requesting process. So in the process you have a number of empty entries in the super block. That is the number of block numbers which are present in the super block is reducing. Then finally I will come to a stage when this super block free block list will be empty. And that is the situation when this block number 71 is to be allocated. Okay. Now when I come to a situation like this, that the block number 71 is the last block number present in the super block, is to be copied into the super block. Now, once I copy this, you find that the remaining part of the linked list is undisturbed, because this block number 110 will go to this location in the super block, okay, and this 110 is pointed to block number 110. So as if what we are doing is we are pushing this entire linked list upwards so that the super block is filled up by this. So the remaining part of linked list remains undisturbed. Okay. So once you do this, then this block number 71 can be given physically to the requesting process. Okay. So you can write an algorithm in the same manner for allocation of disk blocks like this. This is an algorithm, say alloc for allocation of disk blocks. And for allocation of disk blocks, what is the input that is needed? You need the input as file system number, from which file system the disk block is to be allocated. Because right now we don't have to give any specific number of the disk block, because we are not interested in any particular disk block. We are interested in any free block. Okay. So the input will be the file system number, because we want to have a free data block from that file system. Okay. And what will be the output? It is not only the data block, because whenever a process has requested for a block, that means the process will use that block for writing some data. Okay. So whenever the process wants to write some data into a data block, we have said that the process does not directly write to the data block. The process writes that into buffer. Then from the buffer, it will be written back onto the disk block when it is needed. That means along with the allocation of the data block, there must be a buffer which should also be allocated to the requesting process. Okay. And that buffer will have the file system number and block number as the block allocated by this kernel. Because in the buffer we have seen that in the header area you have file system number and block number, and depending upon file system number and block number, the buffer goes into one of the hash lists. Okay. So whenever a disk block is allocated, simultaneously a buffer has to be allocated. Okay. So this disk block along with the buffer has to go to the requesting process. Okay. So the algorithm will be something like this. As before, we'll do it this way, that while super block locked sleep on event super block So this block allocation algorithm will work like this. First, you have to check whether this super block is locked or not. So while the super block is locked, the process has to go to sleep mode, because unless the super block is freed, you cannot get a free block number from the super block. Then if the super block is not locked, then remove block number from super block free list. Then as I said, that when you remove the block number from super block free list, if that is not the last block number, like this, so in this case the last block number is 71. So if it is not the last block number, in that case this can be readily given to the requesting process. So after removing the block number from super block free list, if this removed block is not the last block in the list, in that case you directly come here, okay, and you have to get a buffer for the block that has been removed from the super block list. So if it is the block number 40 or block number 41, it is not the last one. In that case, for getting this buffer, what the algorithm that has to be invoked is the get block algorithm that we have done in case of the buffer management. Okay. So this get block algorithm will get a buffer for this block number which has been removed from the super block list. Naturally, in this case, this block number will not be available in any of the hash queues, because earlier this block was free. So possibly it was not, and that is true that it was not read by any of the processes. So this block will be free and it will not be found in any of the hash queues. So naturally, one of the free buffers has to be taken from the free buffer list and to be allocated for this particular block number. And that has to be done by this get block algorithm. Then you have to initialize the buffer content. That is, you have to set different fields in the buffer, and the buffer has to be put in the proper hash queue. Then because you have taken a block from the free block list, so the total number of free blocks available in the file system has to be decremented by 1. After that, you have to mark that super block has been modified, and the buffer that you have obtained for this block has to be returned to the process. On the other hand, if the block that was removed from the super block list is the last block, so in this case block number 71, in that case, as we said, that the content of block number 71 has to be copied into the super block. Then only this block number 71 can be given to the requesting process. So if removed last block from the list, in that case I have to modify the super block, so I lock the super block, read block just taken from the free list. So in this case it is block number 71 in this example. Copy the block numbers into the super block. So this is content of block number 71. So the entire content has to be copied into the super block. And for doing this, obviously some buffer was allocated for this super block, because this is nothing but a block read operation. So for copying this, read the block just taken from the free block list, the algorithm that has to be invoked is block read algorithm. Okay. Block read algorithm invokes get block algorithm. You might have remembered that. So that get block algorithm gets a buffer for this block which is to be read, right? So that buffer has to be released. So you release the block buffer which was allocated to this particular block. Then the super block has to be unlocked, and after that you wake up the processes which were sleeping on the event that super block is not locked. Okay. So this is the entire set of operations or sequence of operations that has to be done for allocating a free disk block to any of the process that is requesting for it. Okay. But what is more important is when a process releases a block, maybe due to reduction of the file size or maybe due to deletion of some of the files. If you reduce a file size, then while reduction, if any block becomes free, that block has to be returned to the free block list. It has to be entered into the linked list. Similarly, if the file is deleted, if any of the files are deleted, then all the blocks which are allocated to that file, they are freed and they must be returned to the linked list structure. Otherwise, it can never be accessed. So that is more important part. And what you have to do is, whenever a block is released, first we try to see whether the block can be put in the superblock list or not. So if we have a situation like this, that I have any free entry in the superblock free block list, you just place this new block number in that free entry. That links that block into this linked list. But in case you find that the superblock is not empty, there is no free room in the superblock to contain this new block number, then what to do? Okay. So there the simplest procedure is, suppose you remove, say let us take a situation that this is what we have now. So all the entries in the superblock are full. And in this situation, suppose a process releases, say, block number 500. Okay. First, we have to try to see whether this block number 500 can be placed in this superblock. So if there was any free entry, okay, suppose this position was empty, block number 40 has already been allocated. So if this position becomes empty, block number 500, the serial number 500 can be placed in this location, and 500 is linked to this particular linked list. But if the superblock situation is like this, that all the entries in the superblock are full, so I cannot place 500 anywhere in the superblock. So what I do is, I take this block number 500, copy the content of the superblock into this block number 500. That is, block number 500 will contain all these entries, 40, 45, and here you have 71. Okay. In the superblock, you simply put block number 500. These positions are empty entries. Okay. So you find that this becomes a link, block number 500 becomes a link. Block number 500 is now a link block, which links to other blocks in the free list. Okay. So this is the simplest procedure what can be done. So in case there is any free entry in the superblock, you simply put the block number which has just been released into that free entry. But if the superblock is full, there is no free entry in the superblock where this new block number can be placed, you make this newly freed block as a link block. Okay? Copy the content of the superblock into this link block, and this block number you put in the superblock free block list. Okay. So now you find that once you do it like this, next time any process requests for a new block, it will come to this block number. It will find that superblock contains only block number 500, and that is the last block present in the superblock. Okay. So before allocation of this block number 500, the entire block content of the block number 500 has to be copied into the superblock. After that, block number 500 can be allocated. So what we come to this original situation. This entire thing, this is now the content of block number 500, will be copied into the superblock. So that is the situation. Okay, and the remaining things remains undisturbed. So again, the block number 500 will be allocated to the process who has requested for it. Okay. Now initially, when the make file system such a system function organizes all the free blocks like this, you find that normally the free blocks are kept in sequence. If 41 was free, then after 40 there would have been entry for 41, then 42, then 43, then 44, and so on. The reason being, whenever the kernel allocates disk blocks to the requesting processes, it tries to see that as far as possible the blocks are from the same neighborhood. If you allocate block number 40, next time you allocate block number 41, then you allocate block number 42. Unfortunately, if the sequence of requests come from the same process, then a process will get a sequence of block numbers which are mostly contiguous, 40, 41, 42, 43 like this. And that improves the performance of the file system to a large extent, because as we discussed, that whenever a block is read, it is quite likely that the next time process will request for the same next block. And if the next block is in the same locality, in the neighborhood, in that case, time to access the next block is less. Okay. some amount which is called a seek time. That is the time required to place the head over the block that is requested. Okay. So seek time in such cases will be minimum. However, this is not guaranteed always. If it is only the case of allocation, okay, we can say that the processes get blocks in sequence. But because of such release of blocks, the sequence may be disturbed. Okay. So in a system where you have quite frequent allocation and deallocation of blocks, in that case this sequence will be disturbed heavily, and that will bring down the performance of the file system. That means the average disk access will increase. Okay. To take care of this, there is another mechanism which is called defragmentation. So what you can do is, at a regular intervals of time, you can defragment the disk. So while defragmentation, such things again can be restored. Okay. You can copy the content of one disk block into another disk block and try to arrange the free disk blocks like this as far as possible. Okay. So with this, we stop today.